Today, Arnab. He is a PhD student and a Gates Fellow at Cambridge University, and today he'll be talking to us about stellar rotation and why we should all care about it.
Yeah, thank you. Thanks for that introduction. I'm a final year PhD student at Cambridge, and today I'll speak about rotation, particularly in low mass stars, either in single or binary star systems, and I'll talk about how rotation can affect the evolution of such stars in single and binary star systems, and eventually lead to the evolution of any planets that orbit such stars. How do I change slides? Come here every time. Okay. Right. So I'll give a brief overview of what kind of stars we're looking at. We're looking at stars with mass less than 1.2 solar masses. So such stars have a radiative exterior in their main sequence, also in the pre-main sequence. Convective exterior. So if you have stars with mass between 0.3 and 1.2 solar masses, they have a convective envelope and a radiative core. And less massive stars are always fully convective. So this is the basic structure of stars we're going to look at. We're going to primarily look at stars in their main sequence and in their pre-main sequence. So such stars, because they have the convective exterior, these stars undergo angular momentum loss via magnetic braking. And the structure of such stars is super simple. You have convective envelope, radiative core, and you have this convective radiative boundary, which we call the tachocline. And all of this will be essential later. But stars with such structures have magnetic braking, which can be boiled down into three simple points. You have the spinning exterior plus convection, which drives a dynamo. And this dynamo leads to magnetic fields and also drives stellar winds. Together, so these stellar winds are forced to co-rotate with the star up till a certain distance, beyond which these winds escape freely. And because they escape from a large distance from the star, they also carry away considerable angular momentum. But these winds are super weak, so in most of the times they remove very negligible mass. And before we go into how magnetic braking models the stellar evolution of our stars, let me quickly describe how we model magnetic braking. So we model magnetic braking using an alpha omega dynamo. What a dynamo is, in simple terms, is it's a mechanism with which a differentially rotating star can generate long-term magnetic fields. So we model our stars with an alpha omega kind of dynamo, and it's described as follows. In a steady state, we have these poloidal field lines which get twisted to form toroidal field lines because of differential rotation, and this is the omega effect. And then you have these toroidal field lines which get twisted because of convection instead of turbulence. They form these loops which connect together to form large-scale colloidal fields. This is the alpha effect. So in a steady state, you have always toroidal fields converting to poloidal fields and vice versa. And we model the alpha omega dynamo with the prescription by Tout and Pringle, who gave a very simple model of magnetic alpha omega dynamo for contracting pre-main sequence stars. So such stars are fully convective, but when we model partly convective stars, we take into consideration that the star is partly convective and make due adjustments to the model. And with this, we self-consistently obtain time-dependent expressions of winds and an average magnetic field around the star, with which we calculate the magnetic braking strength. If stars have radiative zones, we model the radiative core also as a solid body, and any shear between the radiative region and the convective region is modeled by the shear described in Zanuri et al. And they made a very simple model to explain cataclysmic variable donor stars, but we're not going to go into that. Now, magnetic braking is also influences the evolution of binary stars. So if you have such a star, we just described single stars like this, if they exist as a binary with a white dwarf accretor, they are called cataclysmic variable stars. So this star is just this donor star here. And this star loses mass to white dwarf, usually in the form of an accretion disk. And magnetic braking also leads to their evolution, but due to tidal locking and Kepler's laws, the evolution is a bit different. Let us look at a few equations as to how magnetic braking works in binary stars and single stars. So in single stars, magnetic braking leads to the spin evolution of the star. So we deal with the spin angular momentum of the star, which is proportional to the mass times the size of the star square times the spin of the star, omega square. And when magnetic braking operates on such stars, it removes the spin angular momentum, which reduces the spin, angular velocity of the star, or increases the spin period. So such stars spin down with time, and this is called stellar spin down. So whenever we're going to discuss a single star spin evolution with our model, we're going to talk about stellar spin down. Now, if the same magnetic braking model operates on CVs, we deal with the orbital angular momentum of the system, which is given by this expression here. And for CVs, the spin angular velocity of the donor star is equal to the orbital angular velocity of the system because of tidal locking. So omega spin is equal to the omega orb, and omega orb is related to the separation, which is A, because of Kepler's third law. So when magnetic braking operates on such stars, it removes the orbital angular momentum of these stars, and this decreases the separation, so the orbit increases, so the spin period decreases, so they spin faster and faster. So although the driving mechanism is the same, the evolution is quite different. Another important thing between stellar spin down and CV evolution is what the structure of the star is with time. So like I mentioned, magnetic braking removes very negligible mass. So the mass of the star in stellar spin down is constant with time. It doesn't change much with time. But if such a star is in a CV, it drives the orbital shrinkage, which leads to the donor star overfilling its Roche and start transferring mass to the white dwarf. So although the mass lost due to winds is negligible, the mass lost due to Roche overflow is significant. So with time, the donor star loses mass. This is another essential difference between CV and stellar spin down. But the idea again is that the driving force is the same, which is magnetic braking. So in the next couple of slides, I'm going to motivate you to look at single stellar spin down and CV evolution in a holistic way. So let us look at CV evolution and stellar spin down side by side. But first, I have here a plot of a very standard CV track. We have plotted the donor mass and the orbital period here. And the track, I'll explain this track quickly. We have a CV donor of mass 1 solar, we have a main sequence star as the donor, 1 solar mass massive, and we put it in an orbit with the 1 solar mass white dwarf accreted, and the orbit is set at 12 hours. And now magnetic braking, like I described, magnetic braking reduces the separation, so increases the spin, so the orbit shrinks from here to here. And at this point, the donor star will overfill its Roche and start transferring mass to the white dwarf. So the mass of the donor star decreases and the evolution happens from here to here. So this is the donor mass. And something very interesting happens here, which I'm not going to talk about now. But what happens is that when Roche overflow is undergoing, the orbit is related to the orbital period. So, and the orbit is also related to the radius of the star. So the more bloated the donor star, the wider its orbit. So if we know the orbital period, we know everything. I mean, radius and the orbital separation. So the evolution happens from here to here. Again, there are several interesting caveats in this track, but we're not going to describe all of them now. Yes.
It's just the answer is right, but the reasoning is not correct. Back 3 slides. One more. Yeah. Okay. So there you're saying, okay, in the end, J orb is going down, therefore A has to decrease.
Decrease.
So decrease because it goes as A to the half, square root of half.
Right.
Actually, okay, that's correct, but it so happens you really have, if you do it correctly, do dj by do a log derivative then j dot over j.
Okay.
Okay. Then there's an m dot donor over m donor, and then mw dot by for all that.
Yeah.
Plus there's the a dot over a.
Right.
And all of them happen to make the orbit expand. It's not just the,
Sure, yeah.
even if you have no angular momentum loss, if you transfer matter from a more massive star to a less massive star, the orbit loss.
Yes, yes, yes. Yeah. So as I was saying, there are several interesting caveats in this track which we are going to gloss over, which we're not going to discuss. What I want to motivate you is the fact that maybe we should come back to this later. So if we take the donor star in a CV and just rip it out of the system and let it evolve in isolation, magnetic braking would still operate in such stars. But this will now slow the star down rather than, just because it's in an orbit, it leads to this interesting behavior. So I guess what I'm trying to say is all of these stars, at the donor star at this stage and this stage and this stage, is actually a single star in an orbit with a white dwarf, still driven by magnetic braking. So at this point, if you just rip the star out and let it evolve, it will spin down with time, because magnetic braking is still operating on these stars. So we can, in essence, study the CV evolution and stellar spin down together with the same inherent physics of magnetic braking. So here we have the spin evolution of single stars with time. So this is the spin evolution with time of a 0.3, 0.6, 0.8, and 1 solar mass star. And we have the evolution in its envelope and in its core. So the envelope is the dashed lines and the cores are solid lines. We're going to discuss this plot in detail later, but I'm just trying to motivate you to study magnetic braking holistically. We're going to come to this plot later. For now, let us look at this very interesting feature at this bottom region here. You'll see that the spin orbit decreases and then slightly increases. So this is a very interesting property of CV evolution. These objects are called period bouncers, and it relates to a very interesting problem that has been open for several decades now. And I'm going to discuss that problem now. The problem is the observed dearth of period bouncer series. So this is the problem that we have tried to address by looking at magnetic braking holistically. So there are several jargons in this title, and I'm going to explain each. So observed dearth is we just don't find them, and period bouncers are CVs that show this very interesting property. And it was predicted in the 80s by Paczynski that if you ignore magnetic braking and just take a binary with around 0.3 solar mass donor and any accretor of any mass, and you evolve the system solely by angular momentum loss due to gravitational radiation, this is an inherent angular momentum sink which operates no matter what the system separation is. But just because there is a power 4 separation, it only becomes dominant when the systems are quite close. If you just evolve the CV with orbital angular momentum loss with the GR, you'll have the system shrinking from here to here and then bouncing. And why this happens is because of the change in the mass radius relationship of the donor star. So when the system is around 0.3 solar mass, when the donor mass is around 0.3 solar mass, the donor star is still an M dwarf. So an M dwarf has its mass almost proportional to its radius. It's certain factor here, positive factor. And we said that for a Roshnov filling CV donor, radius is related to orbit and radius is also related to orbital period. So if you reduce mass, you reduce radius, and then you reduce orbital separation and orbital period as well. So with reducing mass, the orbit shrinks. Up till this region, where the mass radius relationship changes from a main sequence mass radius relationship to a sort of degenerate mass radius relationship. So here you have mass inversely proportional to radius. So if you reduce mass, the radius increases, and so does the orbit and the orbital separation. So the system goes from being a shrinking system to an expanding system. And in this plot, it looks like the system has bounced here. That's why the name period bouncers. And like Paczynski said, it's exactly what we see. We see a spike in the number of systems around here. But what we do not see are systems that go past this point. So the question is, why? Why do we not see any systems here? And this is the observed dearth of period bouncers. No matter how nice and sensitive our instruments are, we just cannot see them. So this is the problem. And before we try to solve the problem, let us see how our tracks behave if we use a proper stellar evolution code to model period bouncers. So this is a stellar evolution track in which we have the donor mass, we have the orbital period, and the evolution happens like this, with gravitational radiation. So the first thing you will see is that the bounce happens at a lower orbit than predicted by Hutchinson. So he says that, so this is not using a stellar evolution code. He says that it bounces here, but in reality it bounces somewhere here if you use a stellar evolution code, right? And one other thing that's important is, as the system is going down this track, continuously the mass transfer rate is decreasing, right? So it's a monotonically decreasing function. Mass transfer rate decreases, and at a certain point, I mean, we assume that the mass transfer rate goes beyond a certain detectable threshold, and beyond which we just truncate the track. So
wait, why is the mass transfer rate decreasing? The binary is getting closer, so the delegation of information is becoming stronger.
Right. If you plug in the equations, yes, gravitational wave radiation is becoming stronger because it's getting closer, but the donor is also losing mass. So M donor is decreasing, but M white dwarf is not increasing because whatever accretes onto the white dwarf is emitted in the form of nova eruptions. So the decrease in A, it's not strong enough. The decrease in M donor dominates over that. So the strength still decreases, and as a result, everything decreases. M dot also decreases. So, right? So
You need a very steep mass reduced relation.
A flat one. Because imagine A, like at the period minimum, A isn't changing, but M donor is.
yeah.
Oh, I see.
So M dot constantly decreases up till a point where we assume that it just becomes undetectable. So we truncate the evolution here. Of course, this undetectability limit is uncertain, so we move it around. But for now, we use some number. Don't need to worry about it. And the number is attained at this point.
On the left-hand side of this diagram, it's obvious that the mass transfer rate increases.
Right.
Because both M is going down and A is going up.
Yes.
On
But
the right-hand side,
it still decreases. Yeah. But we have forgotten about magnetic braking, and any M dwarf, these are M dwarfs. I mean, we have seen in nature that M dwarfs break magnetically. But we do not know exactly the nature of magnetic braking. We know that it works, but there is not a physically motivated formula. People use all sorts of things. And one of those...
What is the structure of this thing on the right side? Is this has had the outer layers stripped onto the accretion disk, or what is this thing on the right structurally? You mean this is what's the radial structure of this object? So this is from here to here. It's a M dwarf kind of star, which is a little bit bloated. Than it's, if it were in isolation, it would shrink a bit because now its outer layers have been stripped, so it's a bit bloated. So its mass is still proportional to the radius, but the radius is a bit larger just because it loses mass. Yeah.
So Ren, because on the right-hand side, that's what I was saying that. Yeah, on the right-hand side, just put J dot gr equals 0, and because all that is happening just by conserving angular momentum by shifting matter. So the reason there's what's driving there is mass transfer, and what's driving here is angular momentum.
Yeah, there's two effects that affect the orbit. One is the angular momentum loss from GR for magnetic braking. The other is the mass transfer.
So if you have to do that correctly, that was the point I was making. If you set it up correctly, then you'll get this.
Okay, so this truncation is where the system.
Let me say another thing.
Of course.
This figure, as is, this figure
yes,
only reflects the mass radius relation.
It's all dependent on the mass radius relationship.
There's no mass transfer or something.
I mean, if you increase mass transfer rate, this will go a bit up, but this qualitative feature is independent of the
rate of mass transfer does depend if it's magnetic braking.
If it's stronger, then everything, that's the next point I'm making. In order to move this bounce from here to here, what we can do is we can just add a factor, kappa, and this factor is a constant, which was used by a guy in 2011, and it was so popular that everyone uses this factor. And if you use this factor, the bounce happens where we want to happen. So observations suggest that there is a spike in the number of systems between 80 to 86 minutes, which is called the period minimum spike. And in order to have the system bounce at the spike, you can just add a constant number. This constant number is supposed to mimic how magnetic braking operates in addition to gravitational radiation. However, there is nothing that says that kappa should be a constant. Just because it was used by someone who produced the bounce properly doesn't mean it works. So the thing is, if you use a constant kappa, what we see is that the bounce happens here, and the system is very nicely detectable in this regime before it becomes undetectable here. So if a constant kappa were at play, we would clearly see systems here, which we don't. What we can also do to correctly reproduce the bounce is to use a kappa that decreases with M2, or which decreases as time progresses. And this is what I discussed with Tony, that if such a thing happens, the system attains the undetectability limit within this spike. And why this happens is because we start with a large kappa and slowly make the kappa 0 where the CD bounces. And this so the evolution is sped up here, and then it slowly slows down till it becomes invisible. And mind you, these are the same detection limits. So based on how we model kappa, we can actually have the system bouncing here and disappearing right here. And this would mean that the systems never reach this region as detectable systems. I mean, the maths is a bit.
When you say detectable, that's just a statement by MDOT?
MDOT, yeah. Yes.
Sorry, presumably you have observations of CVs with periods and masses on the right side of your diagram.
Here, you mean?
Yeah.
Yeah.
Up in the top right area.
Yeah.
There's a decent difference between all those choices of kappa observations.
Yeah. Yeah, so if you plot the observations of pre-bound systems here, you see a lot of scatter here. So all the systems do not fall nicely on a single track. There's a bit of scatter. And that's what actually motivated us to begin with the fact that maybe different strengths of magnetic braking operate in pre-bound systems.
I see.
But they all collectively disappear here. And why we say that, I'll come to that later. Very interestingly, if you plot timestamps on all these tracks, you see something nice. And these timestamps are 100 million year timestamps. So you see that the evolution slows down greatly for this system in which kappa becomes around 0 here. And this makes sense because the driving force, which is kappa, we start with a substantial kappa around 10 and just make it 0 here. This disappears. So the speed of the evolution decreases and then the system disappears. This is more evident in the period M dot plot, which I cannot show it. Again, so the question is, yes, we do explain why we don't see period bouncers here if we use a kappa that decreases with mass. But why does kappa decrease with mass in the first place? Why do we think that this happens? And this comes, the essence of this sort of proposed solution comes from single stars. So we know that magnetic braking is intricately related to stellar activity, and stellar activity is related to the spin of the star. So in like F, G, A, and M type stars, we usually see that the faster a star rotates, the more activities. However, this activity spin relation breaks down if we cross from M dwarf regime to the L brown dwarf regime. So the observations by this paper, Mohanty and Basri 2003, and other papers have shown that brown dwarfs, isolated brown dwarfs, show weak activity despite being rapid rotators. So that means that whatever is driving magnetic braking in M dwarfs should disappear. I mean, there is motivation to believe that such a thing disappears when the star becomes a brown dwarf. And if we use this, apparently it in a way serves as a possible solution to the period boundary problem. Yes.
Yeah, but before we go on to this, I just wanted to ask about what it means for the system to disappear.
Yeah.
So the mass transfer rate gets lower.
Yeah.
Maybe they're not right or they don't know first, but there's still mass transfer happening, right?
Yes.
You take a spectrum, you probably still see emission lines, right?
Spectrum. Okay.
So there are large flux limited or also volume limited spectroscopic samples of CDs looking for period downstairs.
Yeah, but we haven't found any with we have only found CVs with a certain. We have not found CVs with let's say mass transfer around a few times 10 to the power minus 12 solar masses per year. We are limited to a certain mass cutoff, which is quite uncertain, but we certainly have not found the systems that would be here if we assume that these tracks work. The mass transfer rate that would be for the systems here is too less. I think
the reason I'm surprised is that in the original CD models,
yes.
One from the 90s to 2000s, it's just assumed that cap was always 0.
Yes.
And they still predict a population of period boundaries. Right?
Yes. I mean, we also predict, we just truncate it by saying that these systems cannot be detected. And that's the observed birth of period bounds in a sense. We do not say that these systems don't reach there. We just say that they are invisible to us, at least for now. And in order to find them, we need Tony used X-ray luminosity. I mean, in order and a cap on X-ray luminosity gives us a cap on m dot. Right. So that's why that's.
Okay. I mean, so what is the mass m dot you assume for them to be non-detectable?
How? You mean why do we choose a certain?
What m dot did you assume?
So for these tracks we use 10 power minus 11 solar masses per year, but we also work with 5 times 10 to the power minus 12 solar masses per year. This would just move these tracks a bit up before disappearing, but the basic idea stays the same.
So I'm confused actually at this point because in a single star, there is mass loss, and that mass loss carries angular momentum. And that's how you're losing angular momentum from the system, and the star slows down. Yes. Now let's say, yeah, but maybe by time, so the fact that brown dwarfs rotate rapidly and don't have activity means something in the magnetic field is such that it could be 2 reasons. One is they have no mass loss, okay, or they have mass loss, but somehow it doesn't carry angular momentum with it. I don't know which of the 2 you're talking about.
So what they said was that probably the atmosphere is too cool to have. I mean, the corona temperature is too less. That's what they suggest to be the reason why magnetic activity related to spin breaks down for brown dwarfs.
But where does that come into the binary system? Because in the binary system, you're losing matter because of Roche overflow.
Yes, but we lose negligible matter due to winds, but considerable matter due to Roche overflow. Yes. But the winds do carry away a lot of angular momentum because these winds are forced to corrotate up till a certain distance, and then they escape.
No, but in the models that you had, you didn't have any loss to winds.
Yeah, because the winds are.
None of these models is mass.
Yeah, because it's negligible mass that's lost due to winds, but considerable angular momentum.
No, but in your model, do you actually have mass angular momentum lost to winds?
Yes.
Which models?
I mean, these models have their spins tightly locked with their orbits. So if there is any spin evolution, that just translates to orbital evolution. So for example, if we take solar winds, maybe 10 raised to the power minus 14 solar masses per year, this strength would negligibly affect the mass of the sun in Hubble time. But if these winds are escaped from, let's say, 10 or 20 solar radii.
So the question I'm asking, the classical models, in addition to all the things we're talking about, is there another term which says J wind?
Probably. I mean, J wind is just J dot orb.
No,
That's-
no, that's not what you're telling me, it's nothing to do with that. Why?
Yes. I think you're right, J wind is the mass loss rate times some lever arm.
Yeah, that,
Yes.
yeah.
So I guess there's two different terms that you have to calculate in your magnetic braking model. I think Arnab's arguing that even if the lever arm is large, maybe for these brown dwarfs, the m dot becomes extremely small.
Right, as in the classical model was that this is operate, that initially on, let's say, 6 hours, for example, that's what's driving the whole evolution. Okay?
Yes.
Then you reach the so-called period gap, and then there's a change in the whole business, and this disappears right there.
No, it disappears around here. Period gap is at the so period gap is at 0.3 solar mass.
Yeah, but why is there a period? I thought the period gap is related to the structure, change in the structure of the star.
Yeah, that is
which has
another.
then related to the wind and all that sort of
Yeah,
stuff.
that is another
So
problem.
you're saying there's a second period gap?
No. This is
No, this is a second phenomenon now.
yes. So there are two
Okay,
interesting.
What's the explanation for the 2 to 3 hour period gap in your knowledge?
Okay, that's another question. Okay, so there we assume. I mean, so the period gap is at 0.25 to 0.3 solar masses, and for more massive stars, these stars have a convective envelope and a radiative core,
Right.
and lower mass stars are fully convective. So we say that there is a second dynamo that operates at the shear layer, which drives a very strong wind, and this disappears when the star crosses the partly convective to fully convective boundary.
Yes, and do you have a wind there carrying angular momentum after it crosses the period gap?
Yes, but the wind strength decreases because so beyond the period gap, I mean here there is two dynamos, the convective envelope dynamo and the shear dynamo, and the shear dynamo, which is very strong, disappears.
Okay.
So the star sort of slows down and shrinks back, the lunar star, and this is the period gap. And at this point, reconnection happens because gravitation, radiation, and convective dynamo again bring them two together, and then whatever happens. And at this point, even the convective dynamo winds disappear. And that is, again, we do not have a physics-based mechanism for this. We only have insights from single stellar evolution, which say that brown dwarfs apparently have no magnetic braking despite being rapid rotators. So we have no physics that explains this. But we just said, what if we incorporate this in binary stellar evolution? That's the answer. So.
Okay, so the reason, even though they're physically very separate, the wind and the orbital thing, because it's tightly locked, you assume everything scales. That's why the Kappa formulation is okay.
Yes. Yeah. So we do not know the nature of how magnetic braking behaves. We can just model it with the Kappa. It's a simple idea, but.
Sorry, can I have one more question?
Go for it.
Okay, so suppose you can't detect it anymore beyond 10 to the minus 11.
Okay.
Should you still see them as eclipsing systems? Or even arbitrary low M dot?
Sure, but have we seen any?
Also, isn't that, if we haven't, isn't that a problem?
Yes, so yeah, sure. I mean, there are several ideas that can refute this model. First being, if we do see a eclipsing system, which would, and we infer its donor mass and it comes here, well, actually no, because most of the CVs that are detected by accretion rate, X-ray luminosity, and we do predict that these tracks go up till here, but we just say that they are undetectable. First of all, they're very slow, and second of all, they're undetectable by accretion luminosity standards. But if you do see an eclipsing system, sure, it would still be okay. Is that
Yeah, so you're predicting there should be a bunch of
we are predicting
eclipsing systems with
here,
very
yeah.
low mass loss rates.
evolving very slowly.
Those can be found. There are
They're really
searches with
slowly, it's
detail.
almost like the Hubble time,
Sure, yeah.
and they won't exist.
Well, it's not Hubble time exactly, I think. It's still like
Except
what is
5
it?
times 10 to the minus 11. So like that, they.
No, that's yes.
5 times 10 to the minus 12.
Minus 12. Okay.
So that means 2 times 10 to the 11 years to transfer the solar mass. And
Yeah, but the
point
donor
solar
here is
mass.
less.
So the donor here is super small, so the mass transfer rate, so the mass transfer
If I
time scale
divide
is.
that by 10, I get 20 years or something.
No, but but the donor is 0.02, so there's 100 that goes out. So it's 5, 10, 10 per 9.
It's a few gig years. It's a long time.
Yeah, but
So if you want to find this eclipsing, the right reasonable way to do is, this is a cool brown dwarf at this point, cool, somewhat warm. I would say the right way is to look at the neowise data. The eclipse depth will be the radius of the white dwarf to the radius of the brown dwarf squared, so it's a 1%. It's floated, it's bad news, but it's not floated, it's 1%. So it's probably detectable. Someone has to go and look at the WISE data.
Why is
The white dwarf.
No, because I think this, what is the temperature? This would be low. I think the temperature, that's what I was trying to compute. I think this temperature should be quite cold at this point.
But it'll still eclipse the white dwarf.
The only one being eclipsed enough that.
Yeah, it's a white dwarf, that's 1%. I mean, yeah, so it's a calculation. Well, here's a stellar model. He has to compute what is the temperature. And I think my sense is that the short wavelength WISE data would be actually pretty good for this. But it's a little hard search because it's a 1% effect.
If it's 100% accurate, but the white dwarf is not going to be colder than the coldest normal white dwarf.
Yeah, just look where white dwarf's getting eclipsed
I
by
think many people have looked for that. That's what.
Yeah, Jan has done that.
Yeah, so that's why I wonder there's something where this is some of the inverted search. So not sure, but it's.
But it still won't break this model because.
I'm saying if you don't find a lot of those, it breaks the model.
Yes. So if we do an accretion, if we do magically get the power to search this regime in the accretion rate space.
They're not going to agree in rate space.
Oh, okay, right. You're saying even if we do a good search and don't find eclipsing system, right, yes, it would still break the model. But so far, I think most of the series are found using X-ray data. So if we talk about observed Earth of period bouncer, here the observed period bouncers are with X-ray stuff. So this sort of explains the.
Well, since you have this model, you should actually, I think Karim's right, you should actually make a prediction. You should say what is the temperature of the white dwarf?
Yeah.
Lunar star and compare that with actual catalogs and see which is a detectable thing, because this is not it's what you're looking at, a 0.1 solar mass, radius star, and a 0.01. So it should be very good.
Okay. But yeah, this was a letter, so it just gave the idea of solving this problem. Of course, several things can be done. But okay, so now we looked at this. Okay. I looked at this regime now, and of course, several things are unknown. But now let's look at this regime where the donor star is partly convective star with the core and the envelope, radiative core and convective envelope. And in order to understand what happens here, we need to understand how the donor star behaves, the core and the envelope behave in a CV donor. And this has not been done before. People struggle with even single stellar evolutions, single stellar spin down of isolated partly convective stars. So why not look at isolated partly convective stars in isolation? So which brings me to the second problem, the problem of now we need to study, we go back to single stellar evolution and we study the rotation profile of low mass stars. So you're going to study stars that are either fully convective, like N dwarfs, some of the N dwarfs, and FGK type stars. And of course, there's a plethora of interesting features of low mass star spins, and we can talk about all of them, but I'm here only going to mention one property which is super interesting. Many people here seem to be interested in that. It's the overactivity of stars in certain open clusters, and also an apparent stalling in their spin evolution of some stars in open clusters. So open clusters are just clusters of stars which are thought to be of the same age, give or take some error bars. So this cluster that we're looking at is the NGC 6811 cluster and the Precipi cluster. And here we have the plot of the spin evolution of all the stars with effective temperature, which is a proxy for mass, So the mass is increasing this way. And if we plot all the open cluster stars in NGC 6811, this is the blue line, right? And if we predict their evolution after, so the age of NGC 6811 is around 700 million years. Sorry, PRECIPI is 700 million years. NGC is around 900 million years. Maybe I'm flipping them too. But theoretical models suggest that stars that are around here should slow down to have spins that are here, right? But that's what we don't see. We see that the stars in NGC 6811 with mass between 0.6 to 0.8 solar masses have apparently stopped their evolution. Like they are not spinning down with time. And this is called the stall spin down problem. And recent observations like by Kao et al. Have also revealed that such stars have high activity. So these stars are unusually overactive compared to what the theory predicts. And groups have tried to explain this stalling and this overactivity by using internal shear as the driving mechanism. So their essence is like this. So the magnetic braking slows down the envelope of the star, but there is very strong shear that spins up the envelope. So in a way, for these stars, the spin down of the envelope is balanced by the spin up of the envelope. So shear, you need some shear to try to spin up the envelope. And they have made simple models in which the envelope rotates as a solid body, convective envelope rotates as a solid body, and the radiative core also rotates as a solid body. And they use some shear physics to explain all these interesting things. And you'll see that you see the extent of shear that you use to explain this. So you have the spin evolution of the envelope of a one solar mass star, and this is the spin evolution of the core of that star. And you see that shear is pretty high here, and it remains high here as well. And for a 0.75 solar mass, the shear is ginormous, super high. And if they are using shear to explain such interesting things in open cluster spins, you need a good handle on shear itself. However, detailed theoretical models and observations of our sun show that there is essentially no shear, at least radial shear, between the core envelope boundaries. So the core envelope boundary is around here, 0.6 solar mass, solar radii. And these black points are P-mode observations. And these lines are observations by using detailed observations, detailed simulations by using either the Taylor's fluid dynamo or Jim Fuller's model. Although they disagree in the core, in the very core, they generally agree with observations that there is no radial differential rotation in our sun. And although these models are a bit younger than our sun, more theoretical models show that a sun-like star attains core envelope near core rotation at around 50 million years. So the idea is that if we are trying to explain these observations with shear, we need to have a good grasp on shear. We can't just use shear as a free parameter and explain stuff.
That's an incredibly precise estimate, which I can't believe is true.
You mean this one?
Yeah, that's sheer. It's
I don't know. It's.
Are you saying the helioseismic measurement?
Yeah, the astroseismic. I mean, it's basically saying there's zero shear.
This is helioseismic.
Sorry.
This is the sun.
This is our sun.
Oh, so regardless, if we know there is.
Yeah, this is our sun.
This is not an astroseismic. Yeah.
Well, it's using P mode.
Yeah. Sorry, I got confused.
Yeah. So even for our sun, yeah. So these theoretical models predict shear that is too high. That's what I'm coming at. So if we are to explain the core envelope behavior of solar-like stars, we have a twofold problem. We not only need the spins of the envelope to match with well-measured spins of open cluster stars and field stars, we also need the core and the envelope to attain core envelope convergence by a reasonable time that agrees with detailed theoretical models. So this is how we model it. We model it again with a two-zone model, very simple. So the envelope rotates as a solid body with omega n. The core rotates as a solid body again with omega core, and there is shear at the radiative convective boundary, whose magnitude, so the shear acts as a mechanism for transport of internal angular momentum, and its magnitude is given by the difference in the core and the envelope spin. So if this,
Yeah, 5 minutes.
Oh.
One time for questions.
okay, so so I can so, but then there was discussions as well. So. Okay, so I can wrap it up. I can maybe just give a hint of star-planet interaction. Okay, 5 minutes, right? So, okay, we not only need the envelope spins to match with observations of spins of open clusters, we need the core and the envelope to attain co-rotation or near co-rotation by reasonable times, right? And this is not a bad thing. I mean, if we have two avenues to constrain our problems, it sort of becomes better. So, what we did was we used our alpha omega dynamo prescription, made suitable adjustments, a few updates here and there, and now our models, I mean, of course, it has a few free parameters which we can use to adjust the tracks. So if you look at the spin evolution tracks of a 0.3, 0.6, 0.8, and 1 solar mass stars, we see that the envelope spins, or the whole star spins, because this is fully convective, the solid lines agree are in general agreement with the observations of open cluster stars, which are this vertical array of dots, and also the core and the envelope attain near convergence at certain times, which match with other theoretical studies as well. I mean, in semi-empirical studies, but we see that there is the core envelope convergence has an inverse mass dependence. More massive stars achieve core envelope convergence earlier, and this is what other old semi-empirical calculations have also shown. But we got it independently. And and this time scale where the convergence happens is not very strongly dependent on the free parameters. So if we change the free parameters, of course, this convergence will not be very nice, but it will still be asymptotically attaining core envelope convergence. So important finding of our work is this function, which is basically a fit like this. So these stars are where the core and the envelope attain co-rotation or near co-rotation, and we made this nice fit, which goes inversely as m star over m naught and sun. But it also has this important spin dependence, which was not there in previous studies. So our simple study predicted that fast rotating stars attain co-rotation earlier than their slow rotating counterpart. And this was described qualitatively, but yeah, we did some robust, simple analysis to get this. So in essence, if you go back to this slide, most likely the shear that they have used is probably not true. So again, if we have to explain interesting physics in open cluster activity or spins, photo evaporation by the activity of the host star. And I don't have time to describe this, so I'll quickly go through what the idea is. So planets orbiting a host star have these rocky cores, and then there are these hydrogen helium envelopes. But due to stellar activity of the host star, these envelopes can, with time, get stripped away, and what we are left with is either stripped core planets, which are called super Earths, or planets with some envelope, which are called mini Neptunes. And apparently, people have done simulations to see that over time, you will have these two clusters of planets So you have super Earths here and mini Neptunes here, and a gap in the planetary radius with period. And this gap is pretty well known. It's called the radius gap or radius valley. And people and groups have done work to show that this depends on the period of the orbital period of the planet around the host star. But recent observations have said that, I'm not going to go into the details, have said that probably this radius gap also depends on the mass of the star the planet is orbiting around. And this is where our results come into play. We say that, so these are our tracks from the spin down paper, and these tracks, if we extend this track to calculate some stellar activity by using some hand wavy arguments, we see that the fast rotating track, which is this one, and the slow rotating track, which is this one, have very different stellar activity evolution profiles. And this is not captured in these empirical fits that people have been using. And I mean, there is motivation to do such studies, because if you look at the stellar activity observations with Rossby number, which is just a proxy for time, if you think about it, there is a spread in the Rx values here, basically everywhere. But when you make this nice empirical fit, it doesn't take into account this spread. So the idea is to create a good stellar activity model, which also depends on the spin, how the spin evolves in a star. And we were not the first to do it. This has been done before as well. So Tu et al. Did this with their model. So the red line is the slow rotator, the blue line is the fast rotator. And if we use, last slide, done. If we use this, if we use the stellar activity tracks to calculate how the atmosphere of planets are eroded, so X is the ratio of the envelope of the planet divided by the core of the planet. So the core is solid. So X decreasing means the envelope of a planet is reducing. We see that the fast rotating tracks and the slow rotating tracks predict wildly different envelope profiles at maybe Hubble times. You see that planets orbiting fast rotating solar mass stars have almost all their atmospheres stripped, no matter what initial X you start. But this is not true for slow rotating stars. So of course there is a rotation dependent inactivity which can help us shed more light on understanding radius valley better. So with that, I would like to conclude. The motivation behind this was to motivate you to study rotation in a more holistic sense. And we only discussed star-planet interaction, but we can also talk about CNO anomalies in globular cluster, which involve rotation in intermediate mass stars, and magnetism in white dwarfs, which involves understanding common envelope and how. So these are two interesting problems that we work with. But for now, I hope you. Thank you.
Okay, so if you'd still like to speak with Arnab after and continue the wonderful discussion, his email is in the Google Doc they sent out to everyone. Let's maybe do just one quick question before wrapping up here.
Yes.
I don't understand many details, but let me just ask as a curiosity. What's the mechanism that is connecting the stellar rotation with the envelope stripping of the exoplanets?
Oh yeah. Yes. So if we look at this slide, we see that a rotating star will have a certain fraction of high luminosity and high energy photons, and when these hit a planetary atmosphere, they can actually lead to it being evaporated away from the planet. And over time, this would lead to this atmosphere slowly reducing in its mass. So the more active the star, the more envelope stripping that happens. And my idea is that this is related to how the spin of a star evolves. So if we understand spin and we can build a working model of relating spin to stellar activity, we can actually properly quantify atmospheric stripping of planets. That makes sense.
I do.
Okay.
Okay, let's all thank Arnab one more time.
Thank you.